Hi everyone, thanks very much for coming. My name is Rahul Pathak. I run the EMR business for AWS, so it's really a pleasure to be here to talk to you about the service. I'm also here with Scott Donaldson and Clayton Kovar from FINRA, one of our customers. They'll be speaking about how they're using EMR at scale as a petabyte scale data warehouse in their environment. And just before we get going, a quick show of hands. How many people here are existing EMR customers? Use EMR today? Okay, about 2/3. How many people use Hadoop in some fashion? Okay, just about everyone, great. So we'll get started. What we're going to cover is I'm going to give you an update on the latest EMR release. This is something that we shipped last week. We'll then talk about some of the key capabilities of EMR. Some of this will be familiar to some of you, but we'll try and get into some actionable tips that you can use in your environments. We will also talk a little bit about how to lower your EMR costs. So one of the things about AWS is that we want you to spend as little as possible to get the work done that you need to. And so we'll talk about how to get more value out of the service. But really the bulk of the talk is going to be Scott, the Senior Director of Technology at FINRA, talking about how they've been able to use EMR in their environments to run large volume queries on large data sets at scale in a secure environment. And then we will have time for questions at the end. So diving into EMR, I think that most of the room is familiar with it, but essentially we are managed clusters for applications in the Hadoop stack. And really this is anything that's in the Apache ecosystem you can use with EMR. So whether it's Spark or Presto or Hive, HBase, everything will run. We also extend the Hadoop stack with EMRFS, which is a file system that essentially looks like HDFS to the applications. And this allows your apps to extend into S3, which is one of the dominant storage tiers and what we'll talk about a fair bit today, but also into DynamoDB, Kinesis, and Redshift. And so you can run jobs that run across these data stores and run them transparently in your applications. And then we also integrate with the AWS security infrastructure, so VPCs, IAM controls, encryption at the object level that we'll talk about, and the AWS key management service. And from a security perspective, all of the things that you're familiar with in AWS are supported here. We also completed HIPAA eligibility for EMR. That was done in July. And so if you're running applications that require HIPAA compliance, that's also supported, and we're covered under the AWS BAA, and we can follow up on that if you have specific questions. And then EMR also integrates with Spot. Who's everyone familiar with the Spot market? Okay, not as many people. So we'll talk a little bit about what that is and how you can leverage it in EMR as well. So last week we released EMR version 4.1. This was actually turned out to be a pretty big release for us. So we added support for transparent HDFS encryption using the Hadoop KMS that allows you to plug in your own key materials provider. And so this encrypts HDFS data, it encrypts the shuffle in MapReduce and transit between nodes, and it also encrypts scratch space on the local disk, so you can actually run a fully secured local environment. We added Spark 1.5.0, and I know 1.51 just came out, and we'll add that pretty quickly in the next few weeks. And we also added Zeppelin. Zeppelin, if you're not familiar with it, is essentially a notebook-like environment where you can run interactive queries in Spark, do visualizations, and collaborate with other users on the system. We added Presto. Presto is a SQL on Hadoop technology that came out of Facebook. It's Apache licensed, and it can operate SQL queries directly against S3. So it lets you run very large scale there. And we also add support for AirPal, and this is a project from Airbnb, which is a friendly front end to Presto. And then the Hive 1 is in there, Uzi is in there. We added Hue, which is a user interface for Hadoop, and that we improved some APIs for launching and configuring EMR clusters, and so generally focus on ease of use from a development integration environment. And we'll continue to see currency with applications in the Hadoop ecosystem, and then you always have the ability to add anything that's not part of the core distribution using custom install actions. And so if there's custom code that you have or packages or applications, those can all be brought onto the cluster as well. In addition to the distribution, we also added support for intelligent resize. So if, for example, you wanted to launch a 1,000-node cluster, instead of having to wait for 1,000 nodes to become available, EMR will actually just incrementally take whatever capacity is there and start the work on your cluster, and then opportunistically add it as it becomes available. So your time to getting jobs executed is much shorter in this environment, especially if there's any temporary capacity blips. And then on the resize down, what we added was the ability to wait for work to be drained from nodes. So if you want to cut your cluster in half, we will wait for jobs to finish with an optional timeout on half the nodes before decommissioning them, so you can scale down without introducing job latency by having to retry. And then we also, as part of this, added the ability to scale down your core nodes. So in EMR, core nodes are where you have HDFS storage, and you can now grow and shrink your HDFS storage, and we just will replicate onto a smaller amount of space. We'll check to see that you have enough HDFS on your target size to house the data that you have allocated, and in that scenario, we'll be able to resize down. So a lot more flexibility in dealing with elasticity in EMR. So one of the core parts of EMR that makes it interesting and typically different from on-premise Hadoop environments is EMRFS. And so what EMRFS does is it allows you to extend your Hadoop and Apache jobs into the AWS ecosystem. The primary one here is S3. And the biggest benefit of S3 with EMR is that you can decouple your storage and compute. So if you think about classic Hadoop data lakes that might run on EC2 or on-premise, typically your data will get cold pretty quickly, and you find yourself adding nodes to your cluster just to house your data, and those nodes aren't really helping you with compute jobs because you're not using that capacity. And so by separating storage and compute and using S3 directly, you can essentially have your storage grow infinitely independently of your compute at S3 storage rates, so 3 cents a gigabyte a month, about $360 a terabyte a year, which is much lower cost typically than you can achieve with three-way replicated data sitting in HDFS. And S3, as you know, is designed for 11 nines of durability, so you don't need to re-replicate. Once your data's there, it can be used directly. And with EMRFS, you don't have to ingest data into HDFS before you can use it. It can stream directly into your jobs, and so you can stream data in, stream it out, and go that way. And so this allows you to resize your clusters, turn them off, turn them on, without having any impact on your core data sets. The other big benefit is that it allows you to point multiple clusters at the same source of truth, which is in S3. So if you have different departments that want to operate different jobs, they can act in isolation. Their clusters can be charged to their business units and their departments, and they don't affect the core production operations of your environment. This also allows you to split interactive query workloads from ETL-type workloads, and again, gives you more flexibility in how you operate. Another big thing, and Scott will talk about this as well, is it allows you the flexibility to evolve your analytic infrastructure. So if you're all familiar with the Hadoop ecosystem, there's a new version of something every week or two. And some of these technologies are interesting and you want to experiment with them. In an EMR environment, you can just spin up a new cluster with that new technology, operate in parallel on your data with your core production environment, and then once you make a decision about which technology you want to adopt, you can easily cut over from one to the other. So it buys you a lot of future-proofing and option value because you can keep pace as the analytic toolset evolves, your infrastructure can evolve with it without any expensive re-platforming or retransformation of data. And with the EMRFS, we've also done some things to make S3 more performant and easier to use. And so there's read after write consistency, so you don't have to worry about eventual consistency in S3. There's also, we've sped up list operations. So if you think about S3 buckets with potentially millions of small files, listing them as you're doing jobs can take some time. And with EMRFS, I'll talk about what we've done. We've essentially built a map in DynamoDB that allows for very fast list operations. And so that can speed up job throughput overall. And this is transparent to your applications. Again, you're just writing jobs as you normally would and going from there. And then as you know, S3 has 3 tiers of encryption. There's server-side, which is checkbox. There's, you can also do client-side encryption, and you can do client-side with keys that you provide, either from a non-AWS key management system or you can integrate with AWS KMS, and that's all transparently supported through EMRFS. So you can run jobs that will read and write encrypted data using your key provider of choice without having to do a lot of expensive configuration or deal with complexity there. And when we talk about transparent to applications, if you think of a Hive job on HDFS, you've got a path to a local data set. If you're going to S3, it's just a simple matter of pointing to the different location. You're not actually changing anything in how you operate. So you get the flexibility of S3 and decoupled storage and compute without having to change or replumb your applications. And if you're running technologies like Spark, for example, on EMR, they take advantage of encrypted data on S3. You can run secure jobs in Spark through this layer using Spark SQL and have access to the overall ecosystem. You can even write Spark queries that traverse S3, DynamoDB, and Kinesis streams, join them together, and pull those into RDDs. So a lot of flexibility in terms of extending into the AWS ecosystem beyond what sits in HDFS. And with the fast listing layer, it might be a little hard to read, but typically if you've got something like you consider a case of 1 million objects, listing them might take 150 seconds with S3 directly, 30 seconds going through EMRFS. So you can dramatically speed up access to jobs using the tooling that we've provided. And then with EMRFS and support for client-side encryption, essentially in this model, you can encrypt data at the object level going into S3 using a key provider of your choice. Could be your own crypto, could be SafeNet boxes sitting outside of AWS, as I think was talked about in the prior session, or it could be the AWS Key Management Service, which lets you define keys, set up IAM policies for those keys to connect with other services and audit the use of those keys. Those can encrypt your objects. The objects are encrypted using envelope encryption, and the metadata is a pointer to the key, essentially. And EMRFS can then use this transparently to encrypt and decrypt objects transparently for your processing. And so this is capability that's built in and lets you run very secure workloads using EMR. Now, EMR also, HDFS is always available. So when you provision clusters, you designate a certain number of core nodes. Your HDFS exists in that environment. And you can use them for iterative workloads. Typically, if you think about it, S3 is a network access. There's an overhead to that connection. If you're using very small files or a lot of iterative workloads, you're not amortizing that fixed cost of the connection over a large volume of data transfer, so you might see some latency relative to running locally in HDFS. And so HDFS is still available for you for those kinds of jobs. And you may want to consider technologies like Spark and pulling that data into memory for iterative processing of RDDs. That's something that we see more and more. And we provide a S3 distcp utility. So this is a distributed copy from S3 that lets you ingest data into HDFS in parallel from S3 at very high throughput rates. So if you need HDFS, it's there for you. And when you're thinking about storage formats, there's a wide range of choices available to you. Again, all of this can be supported. You choose how you format your data onto on S3 for consumption. Our typical advice to customers is when you're using S3 as your data storage tier, just bring in your raw data in whatever format it's being generated in, and then process it into whatever format you need for the systems that you're going to use to query it. And so this way you have an archive of your raw data. You have a data that's ready in a format for processing. These could be row-oriented or column-oriented formats. Typically, your use cases and the nature of your data will determine what you choose there. So for analytic type workloads, column formats can be great because typically you're operating analytic queries on a subset of the columns in a table. And so you're able to get better performance because you're only accessing portions of the data. Row stores can be great if you're trying to look up all of the information about a particular key. And so those options are all available to you in the S3 environment. And if you've got schema that's evolving, any of the self-describing formats like Avro or Thrift or Protobuf can also help you keep track of schema as it changes, giving you flexibility in that regard. And when you're using S3 as your primary data store, what we recommend is use the Hive metastore and have it running in something like RDS. So that way it's running and persistent and highly available off cluster, and this allows you to then spin up, spin down multiple clusters, point to the same Hive metastore, and then have access to all the tables and data sitting on S3. Other factors to think about are the tool sets that you're using, and so different technologies will work better or worse with different data formats. And as with all things databases, you've really got to just try it out and see what works best. So for example, in the case of Presto in the earlier session, NASDAQ found that with encrypted data, Parquet files worked better than ORC, and it just depends on the technology that you use. And you always have the option to experiment with multiple variants and then set your sights on the ones that work best for your workloads. One other tip when dealing with S3 is that small files can be problematic. We talked about the fixed overhead of getting that data, and so you really want to avoid small files where possible, and typically have files that map to your block size, because ultimately those files will feed into a mapper. That mapper is going to be a JVM. Spinning that up also has a fixed cost, and you want to try and amortize that over larger volumes of data to maximize the overall throughput of the cluster. And with small files, you have a couple of options. You can either shrink the HDFS block size, and that can be done when you're spinning up the cluster or adding nodes to it. Or what we think is the better option is use S3 distcp to combine the files into sizes that are large enough to operate efficiently. I think the default block size we provide in EMR is 128 megabytes, and you want to use that wherever you can. Another tip when dealing with S3 and S3-backed data stores is compression. Generally speaking, compression is the way to go because the savings of the network transfer more than offsets the cost of encryption and decryption. Of compression and decompression. And the choices in that scenario are thinking about, when you're thinking about what compression types to use, ultimately it's a trade-off between time and space. So if you're space sensitive, then you want to use something that compresses more efficiently. If you're time sensitive, you can use something where speed is paramount. The table's there for reference. One other thing to think about is the splittability of your compression. So typically, if you have very large files, you want to think about splittable compression models so that you can provide splits to the mappers and not have to essentially bottleneck while processing one large file, because that data skew will lead to essentially your cluster not operating with as much parallel throughput as possible. You're effectively hotspotting. And then from a cost perspective, we really do want you to spend as little as possible on our services. And S3 as your persistent data store automatically saves, we've seen customers save 70 to 90% relative to keeping data live in HDFS, simply because you don't have to replicate it. You can shrink down your compute. If you're running batch workloads, that compute doesn't have to be always on. So for example, Climate Corporation, which does weather modeling for simulation for selling weather insurance. So they run simulations using soil samples, weather samples to try and predict what they should price their contracts at, and they run these simulations every day. So they actually spin up a several thousand node cluster nightly to rerun the scenarios, process data from S3, simulate, write data back out to S3, and that cluster only runs for a few hours. And so that flexibility with S3 as your data store just saves you money across the board. And with Spot, so we talked about Spot briefly. So the Spot market on EC2 is a market for unused EC2 capacity, and you can get up to a 90% discount relative to on-demand rates with Spot. And essentially, it's a market. So you pick a bid price. The market price fluctuates based on supply and demand. And with EMR, you can build in essentially a bidding strategy. You can pick a max bid price. You can pick the number of nodes you want to operate at that price. And so if you have your cluster sized for 10 nodes because that's your SLA and it gets your job done by 2 a.m., but you want to opportunistically add up to 10 more at 90% off, when that's available, EMR will add those to your cluster. Your job gets done in half the time, and you have a lower average cost per job. And so this is just capability that's built in. And if you're not using Spot for batch processing workloads, you're definitely probably paying more than you need to. So we definitely recommend taking advantage of that. And then if you have steady state workloads for always-on ad hoc clusters or interactive models, then EMR works perfectly with EC2 reserved instances. And we even have customers that will use their instances for app servers during the day, and then at night, when they're not serving as much traffic, they'll bring those instances into their EMR clusters, and we can opportunistically take advantage of that capacity. So wherever possible, you can match costs to your workloads. And now with that, I'm going to turn over to Scott, who will walk you through how FINRA has been using EMR at scale, and then we'll come back for questions. So thank you.
Thank you, Rahul. Before I get started, I just do want to give a great deal of thanks to Rahul and the EMR team. We started on our migration of moving to the cloud, started experimenting about 2 years ago, and really about a year and a half ago, came into it full force of moving our market data. And the EMR team, both in terms of the support, product feature requests, and the engineering staff, have been just top-notch in terms of making this journey possible. So before we get started, let me just give a quick background of who is FINRA and what is it that we do. So FINRA we're a private regulator of the financial markets. We bring in data from all of the equities exchanges, or 99% of the equities exchanges, and over 2/3 of the options exchanges, as well as regulate the fixed income markets. When you look at that from a dollar volume perspective, that represents over $600 billion of trading activity a day, and up to 75 billion events per day that we bring in that we're ingesting. And these rows are typically quite large. They're order reports and very detailed. Some of these records have anywhere from 200 to 300 attributes, and they can be quite wide in terms of the details that we have on that. And currently within S3, we're storing over 5 petabytes of that data currently online, and we continue every day to add more and more to that. What we do with that data is we reconstruct it after the fact. And what we look at are any ways of looking for basically market integrity and looking for malfeasance in the market. So these things can range from items such as layering and spoofing, any sort of market manipulation in that regard, also to items like insider trading and fraud. A recent example of the work that we do at FINRA, there was a big press release a little over a month ago from the SEC on an insider trading case that was over $100 million. It involved 32 traders that ended up being charged between the US, Canada, and in Eastern Europe. And what that was an insider trading ring where some Ukrainian hackers were hacking into newswire services, getting into basically unannounced public earnings announcements, feeding that information back over to traders. They would open up accounts, take an advantage position on that, sell it, and they ended up with over $100 million in illegal profits. What FINRA does is our jurisdiction is not that. That falls into the area of the SEC, the FBI, and other foreign agencies like the FSA, but we're sort of one of the front lines of defense on the US markets in that regard. So in our move to the cloud, EMR is ubiquitous within our architecture. And before we kind of jump into where we're at, we should understand where we came from. One of the aspects of where we are running within our own data center, and it's probably a familiar sort of format that anybody working in big data has, we used a variety of very large either relational databases of Oracle and SAN. We also had a variety of different data warehouse appliances, and we had many of these boxes. One of the issue of bringing in this much data, and on any particular day, the market volatility can change. We can end up with spikes where the volume can literally double in the span of a day or two, and being able to scale to that capacity and provision that much capital is very cost prohibitive. And so what we need to be able to do is we were always optimizing on a couple of different variables of both of space and storage and compute, and often dealing with a lot of trade-offs. And that sometimes are we optimizing for our ETL or for our series of batch analytics, or sometimes we would be disadvantaging in terms of interactive queries because you're optimizing around these other variables as opposed to laying out the data and optimizing as to what is the particular use case that you're trying to do. When we moved over, as we're moving up to the cloud, we wanted to remove and break that constraint. And through EMR and S3, we're able to achieve that. So what we have is that we use EMR literally throughout our entire architecture, everywhere from where we bring in the data to where we are doing ETL and data ingest and ingress and data normalization. We run a variety of batch analytic programs. Every day we're constantly looking at daily, weekly, monthly, quarterly, annually look back periods around this, looking for these items like layering and spoofing and insider trading. And then ultimately what we do with that is generate a series of events that a regulatory analyst looks at, and now they need to actually investigate this. So there's a workflow around this. They have to investigate this, and they use things where we provide various different query clusters. Sometimes they're doing targeted queries, other times they're doing very large-scale investigations, and they need a wide or a very large slice of the market. In that case, we use EMR and Hive, and we put that into a Redshift and create little private data marts for the users, so now they can query on that particular slice. And these slices are taking literally from several trillions that we have in S3, several trillion records, within our database, within S3, putting that, and we create slices that might range from a couple 100,000 rows to actually several billion rows. We've created data marts for individual users that have ranged in the 250 billion, and they're still doing that for an analysis where they're doing that over a range of time. So for us at FINRA, as Rahul was alluding to, it's always about like the data, right? That's ultimately what we're trying to be able to do. And S3 is that durable source of record. And what we do with that is, and then EMRFS provides that consistent view for us. The key for us is what we do is that we've separated what we're doing in terms of archiving the data versus what we do in terms of query for use. And we'll create 2 or 3 copies of that data and have it partitioned in different ways on top of an archival format. And to help manage and orchestrate all of this, FINRA has created what we call our FINRA Data Manager. And actually yesterday, a peer of mine, Tigran, announced yesterday during the S3, FINRA has open sourced its FINRA Data Manager. It's called Herd, and you can actually find that out on GitHub to be able to pull that. And what that does is provides a unified catalog of all of our data objects and data sets across S3 and wherever they're being provisioned. It provides lineage and tracking and usage, and it also allows us to do cluster management. So we've abstracted all of these different services at an infrastructure layer so that we don't actually have to, so individual development teams don't need to be able to be worried about that, and they can focus on the matter at hand of what their particular item that they're trying to develop. Along with that, you have to look at like what is the right file format and what's the right compression. For us, because we're dealing with such volumes of data, within the archive, what we selected was bzip because of the high compression. That's really out there. We keep it in S3 for a short period of time and then move that over into Glacier. And I think at this time we're sitting with not just, we have over 5 petabytes of data just sitting inside of Glacier and several more petabytes over in S3 as we archive this data. Our requirements as a regulator of these financial markets is that we have to keep this data for over 7 years, and we have to keep full fidelity on these records. You can't bring a legal case against somebody and be missing 1 record out of 1,000,000 when you're trying to prove a case. That's the first thing the lawyer is going to point at and get the case dismissed. So that chain of custody and that evidence control is critical and paramount with everything that we do. Once we have that data in archive format, we take a look at what are the usages that we're doing of that data and then put it into the right format and partition it and lay it out for the particular purpose that we're trying to serve. Now, some of the nuances that we have within our data is that we don't get all the data for a particular event date on the date we received it. So we had some unique challenges as we were laying out and trying to partition, looking at that and optimizing our query. So what we have in the equities market, for instance, we have over 20,000 ticker symbols being traded between NASDAQ, NYSE, and over-the-counter. We have over 10,000 firms that are trading on these activities that range from the Goldman Sachs, Bank of America's, and Merrill Lynch's to a mom-and-pop shop that literally, a 2-person firm that operates out of their house that are participants in these markets. So if you're looking at that from a partitioning, we always require a date and or an issue or a firm, typically even with most of our query use cases. That would represent over 200 million partitions, and our data is highly skewed because Bank of America trading in Amazon stock is much higher than some small mom and pop shop trading in an over-the-counter security. So what we ended up doing is that violates the one tenet, which is having small files out on S3. So what we ended up coming up with is a hashing algorithm, both where we grouped the issue symbols into over 100 different buckets and looking at the number of firms. And given the size of that, we ended up kind of like with our sweet spot of trying to have our data file sizes within these buckets to be in the 128 to 256 megabyte range. And that provided us sort of the throughput that we were looking for that optimized within our various different queries. So as you were doing any sort of queries around these, if you were doing a symbol query, you would hit at most 10 partitions plus a late partition. So we get this 0.03% of the data that can trickle in slowly over the course of a year to 2 years. And every day we have to continue to add that into it to make sure that it's relevant within that query. If you were doing a firm query, you would hit 101 partitions as opposed to the millions and millions of partitions that you have. And if you're doing a symbol query, you'd actually hit just 2 partitions, the single one with all of the late data. So one of the things that we had experimented in Hive was actually trying to use bucketing, but that didn't actually work with sort of the multidimensional analysis that we were trying to be able to do with this, nor did it work with sort of union all. What we are doing is that oftentimes we are merging orders information, trading, and quoting, so a variety of different event types, and we needed to be able to union these across different time. So an example of creating that hive table is that we would create it, in our case, we had chosen to use ORC, and this time with snappy compression. So snappy gives you very fast compress and decompress, and we were using ORC with all these partitions, and we would create these, and we would have basically the table name, the event date, and then actually the hash partition, which defined that particular table. Basically, that file then represented that partitioning scheme. Now, what we were competing against, as I was stating earlier, was the data appliances. And so you hear a lot of questions around like Hive and the performance of what you're able to provide. So the incumbent in our regard that we were battling against were the types of queries we were running on our data warehouse appliances. Our initial release that we put out in February of this year, we were in the ballpark. We spent a lot of time partitioning and laying out and testing and tuning both the query and the cluster around this, and we got it within the ballpark, and we were able to go out the door with that. Now, partitioning is great, but literally 3 days before we were going live with this, we were back processing and adding more and more data. Literally, we have tens of millions of partitions in our Hive metastore where we're loading 3 or 4 years worth of this data. And a typical query that we were running, we had embedded the hash partitioning into the SQL query itself so you didn't have to enumerate. Problem with that is that the Hive metastore can actually interpret the pmod functions in terms of that. So what it was doing is that the Hive metastore couldn't do that predicate pushdown. It literally returned millions of partitions back to the Hive server, and all of a sudden a query that was taking 30, 45 seconds now was taking 10 minutes, 2 hours because of the number of partitions it actually had to prune in the Hive server 2 process. So what we ended up having to do is literally 2 days before launch around this is refactor our code and come back in and actually lay out and specifically enumerate the hash partitions. And within that, we couldn't use an in clause because that was just sort of the limitation within Hive. So as you're building this data, you always have to be aware of what are the limitations of the particular tools that you're using and what are the different query use cases around that. Now, putting the data up there is great and being able to query it, but it's financial records and they have to be secure. Nate Salmons was actually from NASDAQ, was in the prior session, and he spoke actually quite at depth at this, and we use many of the same techniques that NASDAQ is doing where they are actually providing this data. One is that we require all of our data at rest to be encrypted, all of our data in flight is encrypted, and all our data inside of a server has to be encrypted. So S3, we had internally walked early on within our process of moving to the cloud, we involved our information security folks, and they came up with the assessment, and we had to sell that not only to our IT management, but our business management, to all the exchanges that we regulate, so NASDAQ, NYSE, the CBOE, as well as the SEC, and to our board of governors, which represents all of the firms that oversee what FINRA does. And what we had found is that we actually believe that running ourselves up on the cloud was actually more secure than actually running it within our own data centers that we were operating, given the amount of data that we bring up and shuffle and move around. One of the aspects that I forgot to touch on within our architecture is that every day that we're very, very transient. We bring up anywhere from 9,000 to 12,000 nodes per day where we're doing these analytics and the batch and the ETL, and those nodes go away at the end of the day. So we're constantly bringing up and shutting down on a daily basis. Once we do have a server up, we're using Lux encryption with a random memory key. And so if we were to have to lose a particular node or lose a server, you've lost that data, but it doesn't really matter for us because the golden source of truth is always sitting down in S3 and it's sitting in those external tables. We just reinitialize the cluster and bring it back up and do it again. And then we also use security groups and IAM. And now with the advent of the Hadoop transparent encryption, that's now in the EMR 4.1, we're going to be evaluating that and looking at taking advantage of a lot of those different features that the EMR team provides for us. Now, we go back to why did we end up selecting EMR in the first place? We had been running internal Hadoop ourselves, and we're looking at running Hadoop up in the cloud. Some of our tables, though, as I was talking of our different events, just one of our tables is over 600 terabytes. To represent that data. So to just put that one table in the HDFS on a set of ET2 clusters would have taken at least 30 D2 8XLs. That represents over $1.5 million in cost annually to be able to operate that cluster. Whereas storing that data on S3 and bringing up and ETLing it or querying it when we needed it to, it was $120,000 is what we're paying effectively on that in terms of the storage and the clusters. When we extend that to our other data sets that we have, we're tripling over the number of nodes of these high capacity nodes that you need. So it goes back to the point of having that separation of the storage versus the compute. We don't need that much compute power for the types of queries that we typically are running, that we don't need that much because the queries age over time. There's most of the volume that they're looking at is over the first few months, but we have to be able to query any of the data that goes back up to 7 years. The other item that goes along with that, you'll always hear the argument of within Hadoop is that you have to have data locality. Now, if you perfectly sort of lay out your data and get it all the data locality, which is a ton of work, you might be able to achieve up to like 2 times performance over what you're doing. In general, where you're just laying out the partitions and working through external tables, what we saw is about a 15 to an 18% degradation in performance in general, unless you were willing to put in all of that extra effort to get perfect data locality within your HDFS nodes. So, the trade-off of that, given the cost, was well worth it of using EMR in S3. One of the other items that we considered to help deal with that, or where we do have our most, it is the most recent data, is typically the most queried data. We debated actually storing that data into local HDFS using S3 disk copy and putting that in there. But that provided an operational issue that as you had that cluster, the partition maintenance, you couldn't actually have a separate Hive metastore around that. It actually had to be on cluster. And so hydrating the cluster with millions and millions of partitions, the initialization of that cluster could actually take hours to onboard that. Whereas if you already connect to an existing Hive metastore, that can actually materialize in a matter of minutes. One of the other beauties of just moving on to the cloud, one of the advantages that we were looking to take advantage of was the ability to move and change instance types, as opposed to when you're running inside of your own data center, the fact that you are basically committed to at least 3 years, maybe 5 years of sitting on that particular hardware platform. We went live initially based on the types of queries and analyzing what we were doing, we went live with one of our query clusters with about 140 nodes using M3 class machines, and that was based on the different types of queries. Now, one of the constraints that we had within our own internal environment of dealing with these appliances is that they couldn't deal with concurrency. We had to build a whole governance around that. They were limited in the amount of data and the record sets that we would, through the application, return to them so that we basically time-shared the appliances across hundreds or even thousands of users asking their different questions. Once we separated this concern and basically unleashed a level of untapped demand, literally it wasn't a move down the curve, it was a shift in the curve, right? It shifted outward in terms of what types of questions they were asking, what size of data that they were asking for, and so we ended up learning from that, and we were receiving various different Hive and query errors around that, and so we started refactoring the code and looking at the various different instance types. The new C34s had came out, and we were testing and experimenting around that, and we actually found that by going with smaller, larger nodes, fewer nodes in your cluster of larger nodes, given the memory and the CPU, ended up having better throughput, and we could actually deliver greater concurrency than what we had. And the net result of that is that we actually now weren't just competing with the incumbent, we were actually beating it. We ended up improving our overall query performance across all of our various different test cases by over 36%. We ended up with a greater level of concurrency. Now we are supporting anywhere from 40 to 50 concurrent queries, where in our old appliances we would support 8 to 10. And all of this at a much lower cost, both of what we were running beforehand on our initial version of EMR and a much greater cost efficiency than what we were doing off of our internal environment. So one of the other aspects is you're always looking at cost as an aspect. That's always a selling point as you're trying to move up data to the cloud, is right-sizing your cluster. In our case, I touched on it just a little bit ago, is that you look at your ETL or your batch analytics, and these things are very, very transient. And here we heavily use the spot market. Typically within our SLAs, we've had very few spot failures. And so when you're architecting your batch analytics or your ETLs, you have to understand that the job may not complete if you get outbid and then the cluster gets taken away from you. In reality, we've seen very few failures within that where that actually occurs. And what you can do is look to bid above the market price or even above the on-demand price, because you only actually pay at the price of what the market is doing as a strategy around that. Within the analytics perspective, what we had to look at was what were a couple of factors. What is the amount of queries that we needed to serve at the low period as opposed to the peak period? So it changes your mentality of how you're trying to architect your solution. Before, we were always architecting and capacity sizing for peak. Now we are looking at what is the minimum that we needed, service level that we needed to provide, and how do we grow up and scale up to the particular use cases that the business is demanding. And if we needed 50 nodes and then we needed to go to 200 nodes, we could easily add that to the capacity. So it was really a balance of what was that minimum set and also what is that minimum that you need to put into HDFS. No matter what you're doing, you still have to have some level of HDFS within your core nodes. That's for various different statistics and logging and all the aspects that kind of run with that. So what we found is so the way you can kind of minimize your cost around that is then going out and reserving your master and your core nodes, that minimum size, and then growing your core and your task nodes up on top of that to scale up. And then when the peak demand goes away, then we scale that back down. Right now, we're doing that primarily on a timing basis, and we constantly monitor and look at that, and we're looking to take advantage of some more of the intelligent resizing capabilities with the new EMR release as we go forward. One of the items that we found is that as we scaled up, you needed to keep roughly about a 5-to-1 ratio. Otherwise, your core nodes end up becoming a bit of a bottleneck with all the logging aspects that you need to be able to do that just HDFS requires. So one of the other things that Rahul both touched on, as well as Nate, and you see this as a common practice in terms of architectures, is basically having a single metastore, and that metastore should be off cluster. The advantages of this are several-fold. One is that you get a high level of fault tolerance in terms of having a multi-zone AZ with your metastore, and that's always on, and that your initialization of your servers is much faster. Now they're just basically initiating a connection to your RDS instance around this, and now onboarding that. Before, if you're trying to set up the metastore as part of your cluster, you're literally, where we are doing millions and millions of partitions, it can take about 7 minutes per day to onboard the partitions, and if you're doing it over a course of a month or a year, that cluster may take hours for it to initialize. One of the nuances that you have to be aware of is looking at the tool sets that you're doing. As much as we would love to have in terms of open source and interoperability between file sets, whether it be Orc or Parquet and the various different tools out there of Hive and Presto, there's nuances and there's differences in the data types and what sort of semantics that they support. Hive 13 is different than Hive 1, which is different than Presto. What we are ultimately trying to be able to have is that one copy of the data, and eventually, these products are starting to converge around some of those nuances around the data types, and as that comes in. But in the meantime, what we do is that we keep a different version. We keep a single metastore on a single RDS instance, but we keep multiple versions of that, and we keep that updated on a daily basis. And a part of our FINRA Data Manager, what we do is as new data comes in or new versions of that come in, that those partitions will automatically get added and updated. And so you as a consumer don't have to deal with all of that maintenance, right? If you are a team that's focused on analytics or batch analytics, you now no longer have to deal with all of that infrastructure and the partition maintenance that you normally would, even if you're running like your own database or swapping partitions in and out of your appliances or your other relational data store. So one of the last points that I guess I'd like to be able to kind of like touch on in terms of best practices is that you have to be constantly monitoring, learning, and optimizing and adapting around this. When we initially went out the door, we weren't doing anything. We primarily had a single queue set up within our EMR, and we were basically clogging the highways. We would have a lot of smaller queries that might be asking for 5,000 rows, 10,000 rows, 100,000 rows, 1,000,000 rows. Somebody would come in and ask for a data set that would actually be like several billion. So everybody's smaller queries would get clogged up behind that. So what we did is that we implemented that, and we basically route the query in terms of the various different queues inside of the EMR cluster to separate that concern. Secondly is that you always have to be refactoring your code. You got to be looking at where are your bottlenecks and redesigning and refactoring and taking advantage of the new tools and the new versions and what comes out and what can you do in terms of like caching or other mechanisms around that. One, always be looking to optimize on your cost in terms of transient clusters. And one of the things that if you're looking at your ETL, your batch analytics, so within Amazon, you're paying on the hour of those servers, take a look at your sizing. The worst thing that you'd want to be able to do is have a job that runs like 62 minutes, when if you added 10 more nodes to it, it would complete in 55. So then you're paying that extra hour on those extra nodes. So if you're looking to optimize on cost, you have to play around with that, and you got to look at what your sizing is and be able to try to manage inside of that. One other item that was unique that we had ran into of running, at least in terms of some of our Hive queries over S3, was basically speculative execution. So some of our queries are very, very long running over the EMR and through S3. And what speculative execution does is that as Hive sees if a process is taking too long, it'll launch a new thread to try to be able to do that. The first process would ultimately finish while the second one was still looking at it, and it would overwrite some of the results. And we picked up on the completion of the first thread, not knowing that the other one was unaware. So it was just basically a little item, and we ended up catching that relatively early on. And some other things you can do is using like broadcast joins in terms of being able to take small dimension or various different fact tables and kind of caching those in there. And you can use things like the EMR step API when you're basically setting up various different job queues, but using items like Uzi where you have more complex jobs. The net result of all of this is that we ended up actually removing obstacles. One of the tenets that we had within sort of FINRA technology is get technology out of the way. It's to empower and provide self-service to the individual business consumers to let them ask whatever questions of the data that they wanted to. I kind of call it the Ganesh effect, who's the remover of obstacles, and that's basically getting technology out of the way and let them do what they want to do. The other aspect is that we've lowered that cost of curiosity. So now what we are able to do is provide multiple clusters and separation of concerns. We have various different business departments, and they are looking at the data in different ways. We have Office of Chief Economist, and they're looking for trends and profiles. We have market regulation that are looking for regularities and events and sequences within the data. And so we can separate those concerns, we can optimize around that, and they can get to the types of queries that they're looking to be able to do. The other aspect around this is that when you're in a fixed capacity environment in your own data center, is that you're always dealing with, I kind of always called it the mainframe effect, you're always shuffling data in and out. We were dealing with a fixed capacity of whatever box, and even as you moved from one box to another bigger box, you were always still living inside of a box. What EMR and S3 has allowed us to do is to get outside of that. Oftentimes, you end up with data fixes or data corrections. You have to reprocess, you have to rerun. There's a whole series of analytics and decisions that have already been made on that, but you still got to meet your production SLAs of all your other daily jobs that need to execute. Before, it was just actually a few weeks ago, we ended up having like a big data correction from one of the exchanges that needed to correct over like 6 months worth of data, which means all of that analytics, all of the ETL that were done on top of that needed to be corrected. And so what that happened, if we were doing that in the old environment, that might have been a 2 or 3 month little mini project to shuffle this data in and out. We did that in the span of 3 or 4 days in EMR, spinning up separate clusters around this and actually executing that, delivering the updated results to the business so they could move on. And the final aspect of this is that you're looking at this and you separate these concerns and look at these different services, you end up ultimately increasing your team's delivery velocity. So we've picked up the pace in terms of what we were able to deliver in terms of business value, in terms of the various different services and features we can be able to deliver. So just to kind of recap, a few of the different items is obviously take advantage of EMR and S3 and resize and definitely take advantage of the spot market. You can save a lot of dollars around that, which makes your finance and your purchasing people very happy. You need to look at always kind of having that shared persistent metastore that's out there. One of the other items, I guess the last two are kind of near and dear to us, is that within this ecosystem, all of these things are changing, and you need to be able to adapt and to move around this. Having your data separated from your compute and being able to adapt and move to different items. Currently today we're using Hive. We have smaller patches of Presto, and we're growing and evolving our use of Presto. We have some smaller patches of where we're using like Spark, and that continues to grow. It allows you to, these engines and these tools are going to continue to evolve. As long as you can run them in a Hadoop environment and put them out there with your data separated, you're not tied to that particular format, and it goes back to how you do that. And ultimately, you need to make sure that you're budgeting time to experiment in terms of looking at these engines, right-sizing the cluster, and optimizing around that. You need to make sure you have that built into your delivery schedules as you're working these items out. Some other related sessions that were out there. And with that, we'll be happy to take some questions. We have a few minutes left.